Hey guys, welcome back to Food for Thought Physics. In our last video, we looked at Newton's three laws of motion, the second of which was this statement here that F equals ma. And before we proceed further, we should first examine what exactly this m in this equation here means. So the m here stands for mass. This statement here is force equals mass times acceleration. And the mass of an object you can roughly quantify as the quantity of matter, which is the stuff that makes up the universe, in an object. So you can essentially think of mass as the amount of stuff in an object, or the amount of matter in an object. However, since this is also very hard to properly define, we can also think of this a little more precisely as the inertia of an object. And in our last video, we mentioned that inertia is going to be the tendency of an object to resist acceleration or resist changes in its velocity. And the more mass something has, the more resistance it has to changes in velocity, or the more resistance it has to acceleration. And we can see from this statement that it seems to agree with this idea, because if we want to accelerate some object by some constant acceleration, then it's going to take more force if the mass is greater and less force if the mass is smaller, because we're multiplying this mass times the acceleration. And so mass is going to going to be measured in kilograms. This is the international standard unit here, or the SI unit of mass. And so you might often see that we're measuring something else in kilograms, and this is going to be the idea of weight. We often might see scales measuring weight in kilograms too. And weight is a concept that's related to, but it's not the same as mass. Weight is actually going to be defined as the force of gravity on an object. And this force of gravity, well, we can kind of use this equation here to figure out what that is. As I've mentioned before, we have seen that near the surface of the Earth, falling objects are going to accelerate with some constant g, which is going to be a 9.8 meters per second squared, or 9.8 meters per second acceleration downward. And so, since we know that this is the acceleration of objects near the surface of the Earth, well then, based on Newton's second law, we can say then the force of gravity, which we're going to denote as F sub g, equals mass times the acceleration g of the object, or force equals mg. So now you might ask, well, hold on a second. Isn't this just multiplying the mass by some constant? Why is this weight any different from mass? It seems to just be multiplying it by this 9.8. I can just divide by 9.8 and get the mass then, can't I? Not quite. Mass is a property that's inherent to matter, an object, or inherent to some object. Any object, or some object, is going to have the same amount of mass, or the same amount of matter in it, no matter where it is, or the same inertia and resistance to acceleration. Weight, on the other hand, is a little more subject to change. We know from experimentation and from measurement that the acceleration of objects near the surface of the Earth is 9.8 meters per second squared, but this is not true everywhere in the universe. For instance, if we were on the Moon, the acceleration due to gravity would only be about a sixth of what it is here on Earth, or a sixth of this 9.8 meters per second squared. And we can look more at why this is true in the future. But since this acceleration is a sixth of what it is on Earth on the Moon, or is a sixth of what it is on Earth on the Moon, that means that on the Moon, our weight is also going to be a sixth of what it is on the Earth. While our mass, or this inertia, this amount of matter in us, or the resistance to acceleration, should not change no matter where you are. And so usually, while measuring weight in kilograms, what we're really doing is we're measuring this force and dividing it by g, and taking the amount of mass and displaying it in kilograms. However, a scale, say measuring in kilograms, would correctly display your mass in kilograms if you're on the Earth, because that's what it's been calibrated to do. On the other hand, if you were on, say, the Moon, then it would display a sixth of what it does on the Earth, because it measures weight, not mass. However, your mass actually would not change, so that in that case, the kilogram reading would be incorrect. The correct unit of weight that we usually use is going to be the Newton. named after Isaac Newton. And the Newton, which we're going to denote with an N, is going to be defined as a mass, the standard kilogram, times the standard for the acceleration, which is going to be meters per second squared.